Okay, everyone, welcome back. I'm going to jump right into it today. Before we start, I'm just going to ask you again one more time if there's anything that you need help on today, please reach out to me, whether it's for a one-on-one session or for through email. I feel like this lesson, I'm going to do the best I can to explain it virtually, but without doing it in person, it is a little bit tough, and I can see where it might be challenging for you. So again, I'll do the best I can, but please reach out to me if you need help. All right. We're still talking about area under a curve, and it says how can the area under a curve be approximated algebraically? So yesterday we talked about area under a curve graphically when we added all our rectangles together. Today we're talking about what if we don't have a graph? How can we do it algebraically? Okay, and then check the post for the numbers on the worksheet today. Okay. All right, so next slide, we can use our endpoints along with interval width to determine the actual area under a curve. Okay, so let me just draw a quick visual for you here. Let's say you have a curve, and yesterday we talked about the interval, right? From A to B, let's say we want to find the area under that, we can draw a whole bunch of, rectangles. Okay, whether they're right-sided rectangles or left-sided rectangles, however it might look here. And we can add all those areas together and we can get an approximate area under the curve, okay? So if you need to pause the video, go ahead and pause the video. Next I'm going to start talking about this equation. That's what you want to get in your notes, okay? So that's going to be the equation we're working with today. When you're ready, I'm going to jump ahead. Essentially, what this delta x means. We're seeing a whole bunch of delta x's here, okay? Delta x is just like we talked about yesterday, the distance of the base of each one of these rectangles. It's just a change in your x value, okay? Your delta x is always the same. The base is going to be the same on every rectangle, okay? So essentially what you're seeing here is what we did yesterday. Your x value times your y value. That's the length times the height of your rectangle. Length times the height of your second rectangle. Length times the height of your third rectangle. Length times the height of your fourth rectangle, so on and so forth, okay? That's all this equation is doing, is adding the rectangles for you without actually showing you a picture and drawing it out, okay? As far as how to find the delta x, okay, it's going to be a little bit different today. That is going to be found by subtracting your total interval, b minus a, divided by n, and n is going to be the number of subintervals. And that's going to be given to you in the problem. Okay? All right, so let's give this a try. Example 1. Again, pause the video if you need to write it down. Otherwise, I'll jump right into it. It says find the area under the curve with the given information. It gives us our function, f of x, or y equals x squared, over the interval of 3 to 5, with 5 subintervals using left endpoints. Okay, what does that mean? It always helps on these problems to kind of draw a little quick number line, right? So we're going from, let's say here's 0, let's say here's 3, let's say here's 5. We're going from 3 to 5, and we know that there's some curve above this that we want to find the area underneath from 3 to 5, okay? So, again, using rectangles, we can add all of our areas together and get an approximation, okay? So if we go back to this equation down here, remember that delta x is the width of each rectangle. So what I'm going to do, since the delta x is always the same, what you can do is you can factor out your delta x. So then once you get that, all you need to do is add together your y values of each rectangle, f of x3, so on and so forth, however many there are, okay? So again, your delta x is the same in this equation, so I just factored it out. All we need to find is our y values, okay? So first, we need to figure out what our delta x actually is, right? We're going to have a bunch of rectangles. We would have a bunch of rectangles up here, but we need to know how many or how many spaces there are between those rectangles, okay? So delta x, like we said on the last slide, is equal to b minus a, so 5 minus 3, okay? So this is your a, this is your b, over your number of subintervals, your n. B minus a over n is going to give you 2 over 5, and you can, if you want to change that to a decimal, sometimes that helps to be 0.4. Okay, so what does that mean? It means every 0.4 spaces there's going to be a rectangle. So you've got 3, and then you're going to end up having, let's see, where's a good place to list this out? I would have 3, and then I would have, what, 3.4, 3.8, so 3.4, 3.8, and then 4.2 and 4.6, all the way up until you get to 5, right? Okay, that would be, you've got the 3.4, the 3.8, the 4.2, the 4.6. Let me space these out so it makes a little more sense. That wasn't really good spacing at all. Okay, so you're going to have the 3, the 3.4, 3.8, 4.2, 4.6, and all those are going to be rectangles that go up to meet your curve, so that way you can find the area under this curve. Okay, so again, 3.4, 3.8, so on and so forth. Okay, and how did I get those numbers? I used my delta x. Okay, 0.4 is the distance between these rectangles. That's the length of these bases. Okay, so that gives me this value right here. So I'm going to write 0.4 right here. Now what I need to do is I need to find the height of each of those rectangles. Okay, so in order to do that, we need to know, are we using left endpoints or right endpoints? We're using left endpoints. So on this first rectangle, I'm not going to be using 3.4. I'm actually going to be using 3 because it is a left endpoint on that first rectangle, meaning on that first rectangle, I need to use the left edge of it. Okay, so how do we get that value? What I do is I take the function and I plug in that left value. So f of 3, and what I'm going to do is I'm going to plug it into our function that they give us in the problem. So 3 to the second is equal to 9. Okay, then I need to keep going. Now I need to go to my next rectangle, which is right here, obviously, but I'm using my left edge, so it would be this one right here. Okay, so I would do f of 3.4, and again I would take 3.4 and plug it into x squared, which comes out to 11.56. Okay, I would do the same thing for my next couple of rectangles, f of 3.8. If I square that, it comes out to 14.44. F of 4.2 is going to be 17.64. And f of 4.6 is going to be, when I square that, 21.16. Okay. Here's the key. This is, let's see, 3.8, this was 4.2, this was 4.6. Why did I not do an f of 5? Okay, well it's because in this last rectangle, we are using left endpoints. So that means I used this endpoint right here. Okay, this endpoint right here. I don't want to use the right endpoint. I want to use the left endpoint, which is why I stopped at 4.6. Okay, so what does that do? That gives us all of our f of x's. So what I would do to get my final answer is I would add all these up, 11.56, 14.44, 17, whoops, yeah, I'm good, 17.64, and then 21.16. Okay, when you do this in your calculator, you add these all together and add by 0.4, you get your area is equal to 29.52, I'm going to say units squared. Okay, what I think I'm going to do just to save some room on this video, I think, is I'm going to chop this up into 2 videos. So I'll stop after example 1, and I'll make a separate video for examples 2 and 3.